Hello everybody, welcome back to Math 251. Hope you are having an excellent day. So far this week we have been learning all about derivatives and how to find certain derivatives. So far we can find the derivatives of polynomials, functions involving e to the power of x, and then on Wednesday we learned the product rule and the quotient rule. So now we can take the derivatives of products of polynomials or things with e to the x as well as quotients of them. Today we are going to add something else to our repertoire, trig functions. I know trig is everybody's favorite. Actually, trig is my favorite, so I'm pretty excited about this lesson today. We are going to learn all about trigonometric derivatives. But first, our mathematician of the day is Katherine Johnson, who is one of my personal favorites. She's amazing. She was a black mathematician whose calculations of orbital mechanics for NASA were crucial to our space flights, including our mission to Mars. Her life and work was featured in the movie Hidden Figures, which is a wonderful movie that I highly recommend. And sadly, she actually just passed away this year. I think she was close to 100 years old. So she lived a wonderful life, and she was an awesome mathematician. And did you know that the ancient Babylonians created an intricate tablet containing a huge list of Pythagorean triples? Pythagorean triples are numbers like 3, 4, 5, 5, 12, 13, integer numbers that form perfect right triangles. So it's pretty remarkable that the ancient Babylonians knew all of these Pythagorean triples. Incredible. All right, today we are going to be discussing, like I said, derivatives of trigonometric functions. And the first thing that we are going to do is kind of a tricky proof that will, not proof, but a tricky problem that will help us to understand some problems in the textbook. So we are going to look at the following two limits, and they will help us understand trig definitions and limits a little bit more. So the following two limits are valid and real. So let's write them down. We have the limit. Oh, I don't want that. Sorry, let's change this up. All right, so the first one is the limit as x approaches 0 of sine of x over x is equal to 1. And actually, I can do another version of this. The limit as x approaches 0 of sine of mx, where m is a number, over mx is also equal to 1. So that is our first limit. These are just two versions of the same one. We also have the limit as x goes to 0 of cosine x minus 1 over x equals 0. Now, these three limits you don't need to memorize or anything like that. They won't really come up at all besides this problem that we're going to do, but they are helpful for this next problem and discovering how we can do trigonometric limits. So again, you don't need to memorize these or anything. They're just helpful. So in our first example, we want to evaluate the limit as x goes to 0 of sine of 3x over sine of 4x. So I'm going to be using one of these two rules here. My first step here is I want to divide the numerator and the denominator by x in order to make it look more like one of these rules that I just wrote down. So we first divide the numerator and the denominator by x. So this gives me the limit as x goes to 0 of sine of 3x over x divided by sine of 4x over x. All right, well, it looks like I'm going to be using this one of my rules, but in order for me to do that, I need the same number in front of my x here as I do here. So in order to do that, I am going to divide and multiply the top by 3 and divide and multiply the bottom by 4. So let's see what that looks like. So I'm going to divide and multiply top by 3 and the bottom by 4. So when I do that, I get the limit as x approaches 0. So I'm going to be multiplying this guy by 3 over 3 and this guy by 4 over 4. The reason I'm allowed to do this is because I can divide or multiply fractions by any form of the number 1 that I want to. Well, 3 over 3 is 1, and 4 over 4 is also 1. So basically, I'm multiplying this whole fraction by just 1 over 1. So this is legal. So when I do that, I get 3 sine of 3x over 3x divided by 4 sine of 4x over 4x. Well, according to my rule up here, this guy, I see that this is equal to 1 and this is equal to 1. So this just becomes the limit as x goes to 0 of 3 times 1 over 4 times 1, which is equal to 3/4. So we had to pull out some fancy tricks here, but this is kind of a good reminder as to where some of these funky trigonometric limits come from. All right, next we are going to learn the derivatives of sine of x and cosine of x. Now, if you were to plug in sine of x and cosine of x into our definition of the derivative, the stuff like as x goes to a or as h goes to 0, you would in fact get these derivatives. So the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. So I do recommend memorizing these as we will be using them throughout the rest of the term. They're pretty easy to memorize, except you have to remember this negative right here. So let's use these derivatives and the product rule in order to do number 2. So we want to calculate the derivative of e to the x times cosine of x. Well, I have two terms that are being multiplied together, so I need to use the product rule. So I'm going to label my f of x as e to the x, and my g of x equals cosine x. And then I also need f prime of x, which is just e to the x. And g prime of x, according to what I just learned up here, the derivative of cosine of x is equal to negative sine of x. And then remember, the product rule says that the derivative of f of x times g of x equals f times g prime plus g times f prime. So if I plug all of my pieces in here, f of x is equal to e to the x. That's this guy. G prime is equal to negative sine of x. And then I have plus g of x, which was cosine of x, times f prime. You can leave this as is, absolutely. I'm going to factor out an e to the x from each of these terms, since that's pretty easy. So I get e to the x times negative sine of x plus cosine of x. And that is the derivative. So here we used the product rule, and we used the trigonometric derivative of cosine of x in order to find this. All right, I would like for you to pause this real quick and try number 3 on your own. This will require you to use the quotient rule as well as some of the derivatives that we just learned above. So go ahead and give it a try. All right, let's try this one out. So I'm going to have to use the quotient rule. And with the quotient rule, I have my top function labeled as f, which is 1 plus sine x, and my bottom function labeled as g, which is 1 minus cosine of x. Then my f prime of x, well, the derivative of 1 is just equal to 0, and the derivative of sine of x is equal to cosine of x. Then g prime, again, the derivative of 1 is equal to 0. And then I have the negative derivative of cosine of x. Well, the derivative of cosine of x is negative sine of x. But because I have this negative in front, this becomes positive sine of x. So then, according to the quotient rule, the derivative of f of x divided by g of x is equal to f prime times g minus g prime times f over g squared. And now we can fill in our pieces. F prime is equal to cosine x. G of x is equal to 1 minus cosine x. And then I have minus g of x, g prime, which was sine of x, times f of x, which was 1 plus sine x. All of this over g of x squared. Okay, so this is correct, but I see a potential for some cancellations. Remember, we have the identity cosine squared x plus sine squared x is equal to 1, and I see that that might come into play here. So I am going to multiply both of these terms out to see if I have this cancellation going on. So when I multiply the first term out, I get cosine x minus cosine squared x, that is the first two terms multiplied together, minus sine x minus sine squared x. All of this over 1 minus cosine x squared. So I see that if I combine this negative cosine squared x and this negative sine squared of x, this gives me, so if I have all of this negative, right, I have negative cosine squared x minus sine squared of x is equal to negative 1. So combining these two terms gives me negative 1. So I'm left with negative 1, and then I have plus cosine x minus sine x over 1 minus cosine x squared. That looks a little bit nicer than what we had before we simplified it. Plus, I wanted to remind you guys about those good old trigonometric theorems that we have, the identities. Okay, let's move on to example number 4. We want to find the derivative of tangent of x. So, how can we rewrite tangent of x? Well, if we think way back to our, to our fun times in Math 112, I see, or remember, that tangent of x is equal to sine of x divided by cosine x. And from here, since I know the derivatives of sine and cosine, I can use the quotient rule. So I set my top function to f of x, which is sine of x, and my bottom function as g, which is cosine. This makes f prime of x equal to the derivative of sine of x is cosine of x, and g prime, the derivative of cosine of x is negative sine of x. So then the derivative of tangent of x is equal to low d high, that is low d high minus high d low square the bottom, and away we go. Well, this pretty obviously simplifies a little bit. So if I were to multiply all of this out, I would get cosine squared x plus, because I have a double negative there, sine squared of x over cosine squared of x. Well, I know that cosine squared of x plus sine squared of x is equal to 1. So I get 1 over cosine squared of x. And what is 1 over cosine of x? We define this to be secant of x, and I have secant squared of x. So the derivative of tangent x is equal to secant squared x. So this is a good reminder. If you ever forget the derivatives that we are about to write down of all of the trigonometric functions, really, as long as you know how to use the quotient rule and you know the derivatives of sine and cosine, you can find the derivatives of all 6 trig functions, since all 6 trig functions can be written as the quotient of sine and cosine, and the number 1, of course. So we are going to now write down the derivatives of all 6 trig functions. So we've already learned 2 of them, and now we just derived a third one in example 4. So the derivative of sine of x, we know, is cosine x. The derivative of cosine x equals negative sine of x. The derivative of tangent x we just found to be secant squared of x. And then we have 3 more. The derivative of cosecant is equal to negative cosecant x cotangent x. The derivative of secant x is equal to secant x tangent x. And the derivative of cotangent x is equal to negative cosecant squared of x. So again, the most important ones here are these first 2, cosine and sine, because we can write the other 4 as a quotient of either of these 2. So if we forget them, say on an exam or something like that, we can easily use the quotient rule in order to find the derivatives of the other 4. So using this, let's try number 5, and actually I'd like for you to try number 5 on your own first. So find the derivative of secant x times tangent x. You'll have to use the product rule. Go ahead and give it a go. All right. So we are going to have to use the product rule here. So I'm going to label f of x as secant x and g of x as tangent x. This makes f prime of x, the derivative of secant, according to my theorem here, is secant x times tangent x. And g prime, the derivative of tangent x, is equal to secant squared of x. So then, the derivative of secant x times tangent x equals f times g prime plus g times f prime. So if I were to multiply all of this out, this becomes secant cubed of x plus secant x tangent squared of x. And I can factor out a secant x from each of these terms. And if I do, I get secant squared of x plus tan squared of x. And this is as simplified as I can get it. This inside here, secant squared of x plus tangent squared of x, looks almost like a trigonometric identity, but we are off by a negative sign. So that's as simplified as we can get. All right, we have one more example. Here we want to find the second derivative of cosecant of x. So I have to find the first derivative, and then I have to find the second derivative. Well, according to the theorem that we have above, I know that y prime is just the derivative of cosecant x, which is negative cosecant x cotangent x. And then from here, I have to use the product rule. So if I label f as negative cosecant x, you could put the negative on either one of these. And I label g as cotangent x. This gives me f prime of x is equal to, well, the derivative of cosecant x is negative cosecant cotangent. So this is negative cosecant x cotangent x, or just positive cosecant x cotangent x. And then g prime, the derivative of cotangent, is negative cosecant squared of x. So y double prime here is equal to f times g prime, f times g prime plus g times f prime. We can simplify this a little bit. My negatives here cancel, and I'm left with cosecant cubed of x plus cotangent squared x times cosecant x. Here I can factor out you can leave it just like this. I just like to simplify a little bit. So I can factor out a cosecant of x from each term, and I'm left with cosecant squared x plus cotangent squared x, which again almost looks like a trig identity, but we are off by a negative sign here. So that is the second derivative of cosecant of x. So I hope you guys enjoyed this lesson. I really like trig functions, so I think that this is a pretty cool lesson. And like I said, don't feel too bogged down with memorizing all of the trig functions. Once you use them a bit more, they will just come naturally in terms of memorizing them and everything like that. I think the important thing here is just learning how to utilize the product rule and the quotient rule with other functions like trig functions. So that's it for today. Have a great weekend, and I will see you on Monday.